Welcome to Cybersecurity Under Pressure. Real attacks, real lessons. Every breach starts with something small. A trusted login, a missed alert, a system no one thought could matter. Here, we follow the incident. How it began, how it moved, what broke under pressure, and what security engineering and business teams should learn before the next one. Because the next attack will not wait for a perfect plan. Now, let's follow the evidence.
I gotta tell you, imagine sitting in a sterile, brightly lit control room at like 2 in the morning.
Oh, I've been there too many times.
Right, so you're there and you're staring at this massive bank of monitors, and the screens are telling you that the city's water supply is perfectly fine.
Everything is in the green.
Exactly. The pressure is nominal, the chemical mix is balanced, the pumps are just humming along.
Yeah.
But a mile away, out in the actual physical world,
Yeah.
invisible lines of code are actively dumping lethal amounts of sodium hydroxide, basically lie directly into the drinking water.
God.
And your screen. It's completely lying to you. I mean, it's feeding you this looped, fake reality while the physical process is quietly manipulated toward a mass casualty event.
Yeah.
That is not some Hollywood movie plot. That is the actual terrifying reality of modern industrial cyber warfare.
Man, just thinking about that scenario makes me need a very stiff drink, or, at the very least, a massive amount of caffeine.
Wood incoming. I got you the dark roast.
Oh, thank goodness.
Extra shot, too. You look like you absolutely need it today. How was the weekend?
Oh, man, thank you. The weekend was, well, I basically spent my entire Saturday staring at a packet capture from a 20-year-old compressor station.
Wait, a compressor station in the middle of nowhere?
Yes, out in the absolute middle of nowhere. A device that is supposed to be, completely isolated.
Right.
And yet somehow it started trying to establish a connection to an external command and control server.
You are kidding me.
Nope. A server belonging to a known advanced persistent threat group. So, living the dream. I am running on fumes, stale donuts, and sheer paranoia at this point.
Good morning. Welcome to Cybersecurity Under Pressure, Real Attacks, Real Lessons. Today is Monday, June 22nd, 2026. Shout out to our friends in the United States.
You can't make this up. Well, you could, but nobody would believe you.
I mean, seriously. We are dealing with a reality where the physical world around us, the water we drink, the power grids keeping our lights on, the manufacturing plants producing, well, everything we consume.
The literal pipelines moving fuel.
Yes. All of it is actively under siege. And, okay, let's unpack this, because what's wild to me as we dig into these sources today is that the traditional IT security methods we've relied on for decades are completely failing these industrial systems.
Oh, entirely. They're basically useless.
They aren't just inadequate. In some cases, as we'll see, they're actively breaking the systems they're supposed to protect.
Which is the ultimate irony, really.
So that is our mission for you today. We are taking a deep dive into a massive stack of security advisories, vendor white papers from Drago, Sentinel-Alone, Secamia, and all these various regulatory frameworks.
It's a lot of reading.
It is a massive stack, but we are going to figure out why industrial networks are breaking down, how attackers are bypassing supposedly impenetrable defenses, and how we can actually fix this architecture before something goes boom.
And we really need to emphasize that boom is not a metaphor here. We are talking about literal explosions, environmental disasters, and direct loss of human life.
Yeah,
The stakes are fundamentally different than, say, a data breach.
exactly. It's not just a credit card getting stolen. Let's start by unpacking the original illusion of safety in industrial control systems, or ICS.
The big lie.
Right, because for a long time, the industry relied on this concept of absolute isolation.
Right, the infamous air gap.
The air gap, the idea that if a network isn't physically connected to the internet, it can't be hacked.
It is the biggest myth in modern cybersecurity, but, for decades it was absolute gospel.
Because it made intuitive sense, right?
Exactly. Historically, the entire concept of operational technology, or OT, was built on this foundation of implied trust. Decades ago, the engineers who built these systems, these massive turbines, chemical mixers, water pumps, designed them to be totally isolated from the outside world.
No internet.
No internet, no corporate network connection at all, just a closed physical loop. So their core assumption was that no malicious actor could ever enter bad commands.
Because to do that, you'd have to physically break into the plant.
Right, you'd have to walk past the armed guards, find the actual programmable logic controller on the factory floor, and plug a serial cable directly into the machine.
Which obviously nobody was factoring into their network design. I mean, you don't build software firewalls to protect against physical commando raids. You build fences.
Exactly. Fences and locked doors. They were designing for reliability, for physics, for continuous uptime. They were absolutely not designing to defend against state-sponsored actors probing their networks from 10,000 miles away.
Makes sense for the time.
Yeah, but because of this design philosophy, ICS devices historically did not have any of the protections we take for granted in IT. There are no complex passwords.
None at all.
None. There is no tracking of who is logging in. The communications are completely unencrypted.
Okay, I want to try and synthesize what Dragos refers to in their white paper as the M&M model, because I think it perfectly captures the terrifying reality of this legacy architecture.
Oh, it's such a good analogy.
If I'm understanding this right, the idea is that you build this incredibly hard, crunchy outer shell. That's your perimeter security.
Right, your firewalls, your physical access.
Exactly, your badge readers, all of that.
Yeah.
But once an attacker somehow bites through that shell or finds a tiny crack in it, the entire center of the network is just soft, gooey, defenseless chocolate.
That is terrifyingly accurate.
So once you are past the perimeter, there are zero internal defenses. Like no segmentation, no multi-factor authentication inside the plant floor itself.
Zero. Nothing. Once you are inside the OT network, the systems implicitly trust you. A programmable logic controller, a PLC, doesn't ask for a cryptographic token before it opens a high-pressure gas valve.
It just does it.
It just does it. Many of these devices communicate using protocols like Modbus, which, by the way, was invented in 1979.
Wow, 1979.
Yeah. Modbus literally does not have a field in its packet structure for a password. It just receives the command like function code 5, write single coil, turn the valve on, and it says, okay, opening the valve.
Because it assumes you belong there.
Exactly. It assumes you are an authorized operator because you made it past the hard shell.
Okay, so if they were theoretically air-gapped, and the hard shell was supposedly so secure, what actually changed?
Money.
Right. Why are we suddenly panicking about the GUI center? If the systems aren't connected to the internet, how are these state-sponsored actors actually getting in?
Well, what changed is that modern business realized data is money, and convenience is money. You cannot run a hyper-optimized, highly competitive 21st century factory if your equipment is totally isolated in a silo.
You need the data.
The business demands remote monitoring. They demand predictive maintenance.
Like having a vibration sensor tell you a turbine bearing is going to fail 3 weeks before it actually snaps and destroys the machine.
Precisely. That is hugely valuable. But that requires data to leave the plant floor and go up to some cloud analytics engine, so you have the explosion of the Industrial Internet of Things, or IIoT.
Which introduces connectivity.
Right. And crucially, you have the vendors. Let's say you buy a $50 million robotics assembly line from a manufacturer halfway across the world. They will write into their service contract that they demand 24/7 remote access to troubleshoot it.
So they don't have to fly an engineer out every time a robotic arm throws an error code.
Exactly. It's an efficiency play.
So IT-OT convergence. We took the insulated OT environment and basically just smashed it together with the corporate IT network.
Yes. That convergence completely destroyed the air gap. We punctured our own hard shell on purpose.
We did it to ourselves.
We drilled hundreds of tiny holes into it to get the telemetry data out and to let the remote workers and vendors in.
And the data backs this up in a truly horrifying way. I was looking at the 2026 research from Palo Alto Networks we brought in.
Oh, the exposure stats.
Yeah, they analyzed 16 million samples of network traffic and found a 332% increase in internet-exposed OT devices over the last few years.
It's just absurd.
Over 300%.
Because everyone is just plugging things in without thinking about the architecture. An engineer buys a new smart sensor, realizes it has a Wi-Fi card, and says, great, let's connect it to the corporate network so the CFO can see the real-time production dashboard on his iPad.
And boom, the gap is bridged.
They don't even realize they just bridged the gap.
And that leads directly to the ultimate consequence. This is from TXO Networks, their latest finding, and this stat blew my mind.
I know exactly which one you're going to say.
96% of OT security incidents in 2025 originated from IT-level compromises. 96%.
What's fascinating here is the attack path, the actual mechanics of the breach, because the attackers aren't usually executing some highly sophisticated zero-day exploit to hack a water pump directly from the public internet.
They don't need to.
They don't need to. They are sending a basic, boring phishing email to someone in HR or accounting.
Right.
The HR rep clicks the malicious link, the attacker drops a payload and compromises the corporate IT network.
Standard IT ransomware playbook so far.
Right. But because of this IT-OT convergence, because the air gap is dead and the networks are linked, the attackers just scan the internal network and find a bridged connection.
And just walked right through.
They pivot from the IT environment, slide right through that punctured hard shell we talked about, and land directly in the GUI center of the OT network. And because of that, implied trust, it is completely effortless.
Wow.
They harvest a credential from an IT admin, and suddenly they have the power to shut down a pipeline.
I want you, listening to this, to really imagine this scenario. Think about your home network for a second.
Yeah.
You've got your laptop, your smart TV, maybe a smart thermostat.
Yeah, standard stuff.
Now imagine that instead of a thermostat, you have a 25-year-old industrial water treatment controller sitting on that exact same home Wi-Fi network.
A terrifying thought.
This controller has no antivirus. It cannot be patched. It has a default password like admin123 that is literally printed in a public user manual from 2001 that anyone can download as a PDF.
Oh, I've seen exactly that manual.
And it's connected to the web because your IT guy wanted the convenience of checking its status from his couch.
And if a teenager sitting in a basement halfway around the world manages to guess your Wi-Fi password or phishes your laptop, they can pivot to that controller and turn off the chlorine pumps for an entire municipality.
Just from a guessed Wi-Fi password.
That is the stark reality we are living in.
Okay, so if the hard shell is cracking, or rather if we've intentionally drilled 100 holes into it for convenience, how exactly are these networks supposed to be structured in the first place?
Right, because doing it that way is insane.
Because clearly, putting the critical water pump on the exact same flat network as the HR email server is a recipe for disaster.
It's beyond a disaster, man. It's professional malpractice.
Which brings us to the holy grail of industrial network architecture, the Purdue model.
Okay, stop right there. I have to push back on this.
I knew you would.
Because whenever I talk to modern cloud-native security architects in Silicon Valley, they roll their eyes so hard at the Purdue model.
Let them roll their eyes. They think it's a total dinosaur. It was literally invented in the early 1990s. We live in an era of cloud computing, edge AI, distributed ledgers, and zero-trust FAR architectures.
Sure.
Why are we still fiercely defending a rigid, blocky, layered diagram from 1991 that relies on legacy perimeter firewalls? It feels like trying to secure a Tesla using the blueprints for a horse-drawn carriage.
Okay, I will defend the Purdue model until my dying breath, and I will tell you exactly why those Silicon Valley architects are wrong when it comes to industrial control.
Okay, let's hear it.
Yes, Theodore J. Williams and the Industry Purdue University Consortium developed it in the 90s. And initially, you're right, it wasn't even about cybersecurity. It was about defining data flow in manufacturing.
Right.
But the reason we still absolutely rely on the Purdue Enterprise Reference Architecture, PERA, is because it aligns perfectly with the immutable physics of a plant floor. It gives us a hierarchy of trust that cloud architectures completely ignore.
Okay, if I'm looking at this architectural diagram, break down these levels for us. Walk us through how this hierarchy of trust actually maps to a physical factory.
It works from the raw physical world all the way up to the internet. So level 0 is the physical process itself.
The actual hardware.
The literal mechanical world. The steel valves, the robotic arms, the electric motors, the temperature sensors bolted onto a high-pressure pipeline. They don't run operating systems, they are pure physics.
Got it.
Then level 1 is basic control. These are the devices that interact with level 0, your PLCs and remote terminal units, the RTUs.
What do they actually do?
These devices run real-time operating systems. Their only job is to read the sensor data from level 0, process a basic logic loop, and tell the level 0 valve to open or close in milliseconds.
Okay, so that's level 1.
Right, then level 2 is supervisory control. This is where your human operators sit. It's the HMI's human-machine interfaces and the SCADA systems.
So the screens.
Picture a control room with banks of screens showing the graphical layout of the plant. The operators use level 2 to send set points down to level 1.
So level 0, 1, and 2 are the real operational guts of the facility, the things that make the product or move the power.
Exactly. We call that the seller area zone. Then you move up the hierarchy. Level 3 is site operations. This is plant-wide management.
What lives there?
It houses the data historians, which are massive databases that record all the telemetry coming up from the plant floor and the batch control servers.
Right.
And then finally, you hit level 4 and level 5. This is the enterprise network and the external IT network. Corporate email, the ERP systems, handling billing, Active Directory, and the connection out to the public internet.
And the golden rule of the Purdue model is all about the pathways between these levels, right?
Yeah.
The enforcement of data flow.
Yes. The absolute non-negotiable rule of Purdue is this: IT systems never query OT directly. Never. A corporate workstation at level 4 should never, ever be allowed to send a direct network packet to a PLC sitting at level 1. Data must push upward. It's a waterfall. Level 1 talks to level 2 pushes telemetry up to level 3, and level 4 consumes the data from level 3.
But wait, if that's the strict model, how do we account for the IT-OT convergence we just established is completely necessary now? Because we know that data isn't just pushing upward in a clean waterfall anymore.
Right. The real world gets messy.
The corporate executives want real-time cloud analytics. The vendors demand remote access to level 1 to fix the robots.
Right, and that is where the model had to evolve into what we call Purdue 2.0. The biggest addition to the 90s architecture is level 3.5, the industrial DMZ, or IDMZ.
A demilitarized zone.
Exactly. This is the buffer. The Department of Energy and CISA now absolutely mandate it for critical infrastructure.
How does it work?
You put a layer of strict firewalls at the top of the DMZ, separating it from the level 4 IT network. And you put another layer of firewalls at the bottom, separating it from the level 3 OT environment.
So it's a sandbox in the middle.
Exactly. If an IT application wants plant data, it doesn't query the plant floor. It queries a proxy server or a replica historian sitting inside the DMZ. The IT packet never crosses the boundary into the operational environment.
I see the logic, but here is where the theory completely falls apart in the real world. Let's look at the data from Sentinel and CISA.
Oh, the implementation failure.
Yes, they highlight the single most common implementation failure in this whole architecture. Organizations think they are doing Purdue. They tell their auditors they are segmented. But what they actually do is deploy VLAN's virtual local area networks to separate IT and SCADA traffic on the same physical switches. They assign them different subnets and call it a day.
Oh, this drives me absolutely insane. It is the bane of my existence.
Right, because a VLAN is a layer 2 construct. VLAN tags organize traffic. They do not restrict it. If you don't put actual enforced layer 3 or layer 4 firewall rules between those VLAN subnets, a compromised IT laptop can just route its traffic straight over to the SCADA VLAN. It's like putting up a velvet rope at a nightclub and assuming it will stop a runaway tank.
And that velvet rope mentality, that illusion of segmentation, leads to what I think is the most terrifying phrase in our industry right now, the shadow corridor.
Okay, let's unpack this. So if IT sets up a basic VPN for a vendor, they aren't just opening a door. They're basically digging a tunnel straight past the firewalls directly into the PLC.
Straight to the heart of it.
It's like a shadow corridor that security can't even see. Is that how these breaches are actually happening?
Let me share a chilling anecdote that perfectly illustrates this. I got a text snippet recently from an incident response buddy. He was doing a compromise assessment at a mid-sized manufacturing plant. He's digging through the logs, and he finds out that last month, a maintenance tech for a third-party vendor needed to fix a sensor calibration issue. The tech didn't want to drive 3 hours to the plant in the middle of the night, so the IT department, trying to be helpful, set him up with a standard corporate VPN.
Naturally, because IT is measured on resolving tickets quickly.
Exactly. They want to close the ticket. But the VPN didn't drop him into a jump host in the level 3.5 DMZ like it's supposed to.
Uh-oh.
Because they used a flat VLAN architecture without proper firewall rules, the VPN connected his remote laptop directly to the level 1 PLC on the plant floor.
Oh no. Bypassing the DMZ, bypassing the supervisory control, bypassing all the monitoring.
Completely bypassing the entire Purdue segmentation. That IT admin essentially drilled a digital wormhole from the public hostile internet straight into the GUI center of the OT network.
Yeah.
And he didn't even know he had just opened the only door an attacker needed.
So that direct VPN creates the shadow corridor.
Exactly. Rogue devices and lateral movement by attackers can hide inside those perfectly normal-looking VPN traffic patterns. Your intrusion detection system won't flag it because the traffic is encrypted and looks like authorized vendor access.
It looks legitimate.
Your firewall won't see it as malicious because the rule explicitly allows it. It is a dark, unmonitored tunnel straight to your most critical life safety assets.
In the wire transfer, they would kill me for saying this, but relying on legacy VPNs for industrial sites is basically handing the keys to the kingdom to anyone with a fish password. It is stunningly reckless.
I completely agree with you. It's archaic. And it's not just a technical faux pas anymore. The legal landscape is shifting aggressively. Look at the regulatory panic happening globally right now.
Yeah, the rules are changing.
Under the European Union's NIS2 directive and specific national laws like Portugal's Decree Law 125/2025, critical infrastructure operators are facing intense, unprecedented scrutiny.
Yeah, if I recall from the notes we reviewed, that Portuguese law demands incident reporting within 24 hours of a confirmed breach.
24 hours. Think about the logistics of that. If you have a breach, you have to discover it, analyze the scope, contain it, and file a formal report to the government in one day.
Which is impossible if you don't even know what's happening.
Right. If your network is full of shadow corridors because you handed out direct VPN access to every HVAC repairman, elevator technician, and robotics vendor, you have zero visibility. You won't even know you've been breached for 6 months.
And the regulators won't care about your excuses.
Having these shadow corridors isn't just technical debt anymore. It is board-level negligence. If you get breached through one of those unmonitored tunnels, the regulators will absolutely eviscerate your company.
So if these shadow corridors bypass the firewalls, the attackers are bypassing the physical controls and landing right in the lap of the human operators.
Yeah.
What happens when the attacker takes over the operator's actual monitor? Which brings us to the most terrifying part of this whole equation. When the screens lie.
Yeah. This is where things transition from a data problem to a physical safety problem. Because when an attacker is inside and they have access to the HMI, the literal laws of physics are suddenly at their mercy.
Let's clearly define the crown jewels here. The HMI, the human-machine interface. For you listening, I want you to imagine the dashboard of your car.
That's a good way to put it.
It tells you how fast you're going, how much gas you have, if your engine is overheating. The HMI is the exact same thing, but it's the dashboard for a nuclear power plant or a chemical refinery.
It is the only window the human operator has into the physical process. You are sitting in a centralized control room. You cannot see the actual chemical mixing tank. It's a quarter mile away, behind 2 feet of reinforced concrete.
You just have to trust the screen.
You rely 100% on that HMI screen to tell you the pressure, the temperature, the flow rate.
Here's where it gets really interesting and simply unsettling. According to research from SIGA and other ICS security firms we reviewed, the greatest threat to industrial resilience isn't just a system crashing and going offline, because a crash is bad, but it triggers fail-safes. The true threat is uncertainty.
Yes. The nightmare scenario is HMI hijacking.
Because if the system just goes black, you hit the emergency stop button. But what happens when the Chief Information Security Officer, the CISO, and the plant operators look at their screens and realize they can no longer trust the data?
In IT, if you get hacked with ransomware, your screen locks up and a red skull pops up demanding Bitcoin. It's loud, you know you're hacked.
It announces itself.
In OT, a sophisticated attacker doesn't lock your screen. They hijack the communication protocol between the PLC and the HMI. They execute a man-in-the-middle attack, so the HMI feeds you a looped, pre-recorded visual of normal operations.
Oh, man.
The screen says the tank pressure is 50 psi, completely fine. It says the cooling valves are open and functioning. But in reality, the physical process in the background is being maliciously manipulated.
Because they've intercepted the real data.
The attacker has closed the cooling valves, the pressure is building to 500 psi, the temperature is spiking, and the operator sitting in the control room has absolutely no idea until the physical safety valves blow or the roof of the building explodes.
It's literally the digital equivalent of Ocean's 11 looping the security camera footage so the guards see an empty hallway while they rob the vault.
That is exactly what it is.
Let's look at the history of this chaos, because we need to understand that these aren't hypothetical, theoretical, academic exercises. These are real attacks. Let's go all the way back to the year 2000, the Maroochy Shire incident in Australia.
Oh, the sewage spill. The classic insider threat.
Literally a massive sewage spill. A disgruntled former contractor who had actually helped build the system used a two-way radio and stolen control software to hijack the pumping stations.
From his car, right?
Yeah, from his car. Because the system lacked robust authentication, the HMI controls were completely subverted. He sent false data to the central computers and commanded the pumps to ignore alarms. He caused millions of liters of raw, untreated sewage to spill into local parks, rivers, and hotel grounds over several months.
Just incredibly destructive.
All because of inadequate access control and blind trust in the telemetry.
And as bad as that was, it was rudimentary. Fast forward a decade to 2010. Stuxnet.
The absolute granddaddy of them all, the Rubicon moment for industrial security.
Stuxnet was a masterclass in HMI manipulation and process destruction. It targeted the Iranian nuclear enrichment facility at Natanz.
Which was totally air-gapped, supposedly.
Supposedly. It specifically infected the Siemens PLCs controlling the centrifuge arrays. Now, a centrifuge spins at supersonic speeds to separate uranium isotopes. It is an incredibly delicate piece of physics. Stuxnet would subtly alter the drive frequencies, spinning the centrifuges fast enough to destabilize and tear themselves apart, but then slowing them down to normal speeds, so it looked like standard random mechanical failure. But the genius, the truly evil genius of the payload, was the intercept mechanism.
Explain how it blinded the operators, because this is wild.
The malware essentially executes a replay attack. It recorded 21 seconds of normal operational data from the plant floor.
Wow.
When it began to execute its destructive frequency changes, it intercepted the real telemetry data coming up from the sensors and replaced it with that pre-recorded loop.
So the operators just saw the loop.
The operator's screens in the control room showed that every single centrifuge was operating at perfect, optimal parameters. They had no idea the facility was physically destroying itself until they walked onto the floor and saw the broken machinery.
And the operators just sat there, trusting the lying screens. Then we see this evolve. We have the Ukraine power grid hack in 2015.
That one was incredibly brazen. State-sponsored attackers gained remote access through phished IT credentials, pivoted through a shadow corridor VPN into the OT network, and seized direct control of the SCADA HMIs.
They just took over the mouse.
Literally. The operators sitting in the utility control rooms had to take their hands off their keyboards and watch helplessly as the mouse cursor moved across their screens on its own, clicking breakers and intentionally plunging 225,000 people into the freezing darkness of winter.
That is nightmare fuel.
And to add to the chaos, the attackers ran a destructive wiper malware called KillDisk to permanently destroy the workstations and launched a coordinated denial-of-service attack against the utilities' call centers, so panicked customers couldn't even report the outages.
So they blinded the operators, destroyed the equipment, and deafened the response teams. But if we're talking about the ultimate escalation in this timeline, it has to be 2017. Triton, also known as Trisis.
Triton changed everything. It sent a shockwave through the entire OT security community. Because Triton didn't just target the process control PLCs, it specifically targeted the safety instrumented systems, the SIS.
Right, the safety nets.
Specifically, the Schneider Electric Triconics controllers.
For the listener who isn't an engineer, explain why targeting the SIS is a massive, terrifying escalation.
Yeah.
What exactly is a safety controller?
The SIS is the absolute last line of defense in a physical plant. If the primary control system, the normal PLCs, goes crazy or gets hacked, or a valve simply breaks, and the system tries to overpressurize a highly volatile pipeline, the SIS is a completely separate, redundant, hardwired safety system.
It's watching the physics independently.
It watches the physics. If the pressure exceeds the absolute safety limit, the SIS physically trips the breakers, cuts the power, and shuts everything down to prevent a catastrophic explosion. It is the failsafe. Triton was a highly sophisticated malware framework deployed at a petrochemical facility in Saudi Arabia, and its entire purpose was to reprogram and disable those safety systems.
So the attackers were trying to blind the safety net, presumably so they could then launch a secondary attack to cause a catastrophic physical event, and the failsafes wouldn't kick in. They wanted an explosion.
Exactly. To reprogram a Triconics controller, there is a physical key switch on the hardware that must be turned to program mode.
Like a literal physical key.
A literal key. The attackers either waited for human error, an engineer leaving the key in the wrong position, or they found a way to manipulate the memory remotely. The only reason it was caught was because a minor bug in the attacker's card triggered an accidental fault that shut down the plant.
So it was just dumb luck.
Pure luck. A process control engineer noticed unusual behavior on the safety system before a security analyst did. But the intent was crystal clear: disable the safety, manipulate the chemical process, and cause massive loss of human life.
And we almost saw a mass casualty event in the United States in 2021, the Oldsmar water plant in Florida.
Oh yeah,
Uh-huh.
through a remote access software team viewer, if I recall correctly, another classic shadow corridor.
Right. An attacker gained access to an internet-exposed computer that was connected to the plant's control system. They hijacked the HMI, and an operator physically watched their mouse move across the screen to open the chemical dosing valves, changing the sodium hydroxide, which is lye, used in tiny amounts to control water acidity from a safe 100 parts per million to a highly toxic 11,100 parts per million.
They actively tried to poison the drinking water supply of an entire city.
Just unconscionable.
Thankfully, the operator was paying attention, saw the mouse moving, and immediately reversed the command before the poisoned water left the plant. But it highlights the extreme fragility of trusting these interfaces.
So, synthesizing all of this, what does this mean for the fundamental economics of OT security? I mean, in the IT world, the cost of a data breach is usually calculated by regulatory fines, providing identity theft protection for your customers, paying for incident response consultants, maybe some lost revenue from your e-commerce website being down for a day.
It's just numbers on a spreadsheet.
Right. But what is the actual tangible cost of an OT breach?
It is an entirely different financial and moral universe. I was reading a piece in the Industrial Cyber Source material, quoting Jacob Marsloff and a security expert named Oosterink. They articulated it perfectly. In OT, a breach doesn't just expose credit card records. It halts production, triggers safety system failures, damages physical equipment, or endangers lives.
Marsloff emphasized that securing OT is a fundamental business risk decision, not just an IT compliance exercise.
Right. Oosterink pointed out that there is no universal price tag for an OT breach because context is everything. If you hack a retail bank, you steal money. It's a spreadsheet problem.
You could insure against that.
If you hack an oil and gas refinery, as Oosterink says, the cost could be measured in explosions, environmental leaks, and direct harm to human life. If you hack a pharmaceutical manufacturing plant, it's about ruined batches of life-saving drugs, severe FDA regulatory penalties, and total loss of operational compliance.
The scale is just massive.
You might have to scrap $50 million of vaccines because you can no longer legally prove the temperature controls weren't tampered with. The cost is never a simple IT repair bill. It is existential business ruin.
Okay, let's unpack this deeply because this is where the friction really happens.
Yeah.
If the stakes are literally explosions, poisoned water supplies, and ruined drug batches, if the risk is that exceptionally high, why don't we just run standard, proven IT security tools on all these industrial machines to fix them?
Oh boy.
Like, why not just install a modern endpoint detection agent like CrowdStrike or Sentinel-Alone on the PLCs? Why not run automated vulnerability scanners every night?
Man, if only it were that easy. This is the great IT-OT clash. If you bring an enthusiastic IT security engineer onto a plant floor and let him run his standard automated toolkit, he will accidentally shut down the plant faster than any external threat actor ever could.
Wait, really? We need to explain this mechanism clearly.
Yeah.
Why do IT tools break OT environments? What is the actual physics behind this clash?
Let's talk about the extreme danger of active scanning. In the IT world, to find out what devices are on your network and what vulnerabilities they have, you run an active scanner like Nmap or Nessus.
Right.
The scanner sends out millions of probing packets, TCP handshakes, ICMP echo requests to every IP address it can find. It's basically knocking violently on every door and asking, who are you? What operating system are you running? What ports do you have open?
Standard network discovery. It happens 1,000 times a day in a corporate office.
Exactly. In IT, a modern Windows server or a MacBook has gigabytes of RAM and multi-core processors.
Yeah.
It can easily handle a few thousand ping requests a second. It processes the interrupt, drops the unwanted packets, and moves on without breaking a sweat.
It doesn't even notice.
In OT, I want you to remember that some of these legacy PLCs and RTUs have less processing power than the microchip inside your microwave oven.
That's wild to think about.
They were built in 1995. Their network interface cards were designed to handle maybe 10 packets a second. They were built to do exactly one thing: read a sensor and open a valve in a strict, real-time deterministic loop.
So what happens when the IT scanner knocks on their door with 10,000 packets a second?
The PLC's fragile network stack gets completely overwhelmed. The CPU spikes to 100% trying to process all these weird IT packets it doesn't understand. It creates a buffer overflow.
Oh, wow.
The ShieldWorks source material we reviewed is incredibly explicit about this. Never run active scanning tools on live OT networks. It is a literal safety hazard. I have personally seen active IT scanners corrupt the memory on legacy RTUs, forcing them to require a hard manual reset. I have seen them trigger spurious trips in compressor stations.
What's a spurious trip?
It means the machine panics. Because its CPU is pegged at 100% dealing with the IT scanner, it misses its real-time processing window to check the safety sensors.
So it defaults to safe mode.
Exactly. The internal logic says, I haven't heard from the pressure sensor in 50 milliseconds. Something is catastrophically wrong. Shut everything down. It physically trips the breakers and takes the multi-million-dollar process offline.
So the IT security guy literally causes a self-inflicted denial of service attack.
Exactly. You cause the exact operational downtime you were hired to prevent. You become the threat actor.
Okay, so if you cannot actively scan the network, how do you even know what's on it? Because as we established earlier, you can't protect what you don't know exists. How do you find the vulnerabilities?
You have to fundamentally change your approach. You use passive asset discovery.
Meaning you just listen.
Exactly. Instead of sending out aggressive probes, you deploy network tapis, or you configure span ports on your industrial switches to mirror the traffic. You just connect a listening device, sit there, and quietly record the network traffic that is already naturally flowing.
How does that identify the devices?
Protocol-aware OT visibility tools like Dragos or Clarity can fingerprint the devices based purely on how they talk. The software analyzes the packet payloads and says, oh, I see Modbus traffic coming from this IP, and based on the specific byte structure of the response, that's a Schneider electric controller running firmware version 2.1.
It's like standing in a crowded room and figuring out who everyone is just by listening to their accents without ever introducing yourself. No packets injected, no machines crashing.
Right. And you absolutely must deploy these passive tools because relying on manual asset registers, the Excel spreadsheets that plant managers typically use to track their gear, is a fool's errand. They are almost always hopelessly wrong.
Yeah, the field notes from the ShieldWorks report are wild. They state that in typical oil and gas security assessments, passive discovery reveals that 46 to 78% of devices are completely missing from the manual register. Think about that. Over half the network is totally invisible to the security team.
That's terrifying. When you plug in a passive listener, you find horrifying things. You find forgotten 4G modems strapped to the side of analyzer cabinets by vendors. You find undocumented consumer Wi-Fi routers plugged into the wall by operators who wanted better internet reception on the night shift.
A router just hanging off a PLC.
Yes. You find ancient serial to Ethernet converters that haven't been patched since the Obama administration. Every single one of them is an unmonitored attack vector.
Okay, so you listen passively, you find the invisible devices, you map the network safely. But then, how do you manage the actual security governance? Because looking at the literature, there seems to be a massive clash between different regulatory and engineering frameworks.
Oh, the framework wars.
Yeah, why do organizations have to use both the IEC 62443 standard and the NIST SP 882 guidelines? Isn't one massive binder of rules enough?
This raises an important question about how we bridge the communication gap between the engineering floor and the corporate boardroom. IT loves NIST frameworks. OT loves engineering standards. If you pick just one, your security program will inevitably fail.
Break down the distinction for us. Why do we need both?
Think of securing a facility like building a massive skyscraper. IEC 62443 is the prescriptive structural engineering standard. It was written by the International Electrotechnical Commission by actual control systems engineers who walk plant floors and argue with DCS vendors.
So it's very technical.
Extremely. It defines the absolute physics of your security. It tells you exactly how to build your zones and conduits. It requires specific, deeply technical benchmarks categorized into security levels 1 through 4. It's the blueprint for the concrete, the steel, and the fire doors.
And what about NIST?
NIST SP 882, on the other hand, is the descriptive governance overlay. It maps industrial security to the broader NIST cybersecurity framework, the 5 pillars. Identify, protect, detect, respond, recover. It tells executive management how to run the security program, how to evaluate enterprise risk, how to budget, and how to train staff.
So DIST is the project management manual and the building code, while IEC 62443 is the actual structural engineering math required to ensure the building doesn't collapse.
Exactly. You need IEC 62443 to make sure the plant doesn't blow up, and you need NIST to survive an external audit and explain to the board of directors exactly where their security budget went. They are complementary, not competitive.
Okay, but even with the best frameworks perfectly aligned, we eventually run into the patch management nightmare. This is another massive IT-OT clash that just blows my mind.
Patch him.
In the IT world, Microsoft releases Patch Tuesday. Every 30 days, your laptop downloads an update, reboots in the middle of the night, and installs the security fixes. Why not just patch the OT systems on a 30-day automated cycle?
Oh, man. Try walking into a control room and telling a plant manager you need to take down a power generation turbine, halting millions of dollars of electricity production so you can install a Windows security update on a Tuesday afternoon.
I'm guessing that conversation ends with security being escorted off the premises.
You'd be thrown out of the building. In OT, uptime is king. Availability is the absolute highest priority. Maintenance windows, which are the planned turnaround outages where you are actually legally and operationally allowed to turn machines off, might be 12 to 24 months apart.
Wait, 2 years between security patches?
Yes. Because patching a DCS, a distributed control system, isn't just clicking update and hoping for the best. The patch has to be rigorously validated by the OT vendor first.
To make sure it doesn't break anything.
It has to be tested in an offline physical staging environment to ensure it doesn't change the execution timing of the real-time operating system. Because if a patch delays a sensor reading by 50 milliseconds, the physical process might fail. So you test it for months, and then you wait for the annual turnaround outage to carefully install it.
Okay, let's summarize the sheer terror of where we are right now. We have a punctured perimeter full of undocumented shadow corridors. We have fragile legacy gear that will physically crash if we actively scan it to find vulnerabilities. We have critical software flaws that we cannot patch for up to 2 years. And these systems are controlling highly explosive, dangerous, real-world processes where uptime is completely non-negotiable.
That is the terrifying everyday reality for an OT security engineer.
So how do we actually secure remote access for the vendors who must connect to keep the plant running? How do we fix this broken architecture? Which brings us to the core solution, applying zero trust in a legacy world.
If we connect this to the bigger picture, the answer to implicit trust, the answer to the M&M model where the inside is gooey and defenseless, is zero trust architecture.
Let's define zero trust carefully here. The concept originally comes from IT, right?
Yeah.
Google's Beyond Corp initiative back in 2009.
Yes. The philosophy is beautifully simple. Never trust, always verify. You completely abandon the concept of perimeter security.
The hard shell is gone.
Exactly. You don't care if a user is physically inside the corporate firewall or outside a coffee shop. Every single request to access a resource must be strongly authenticated and dynamically authorized based on identity, device posture, and context every single time a connection is attempted.
Oh, wait. We just spent 20 minutes explaining in agonizing detail why modern IT concepts break fragile OT environments.
And this is no exception.
Right. And CISA's April 2026 guidance says exactly that. Blanket application of IT zero trust to OT is neither reasonable nor feasible. Yeah.
You just told me a 1995 PLC running Modbus doesn't even have a password field. You can't put a modern cryptographic authentication agent on a device that communicates in serial protocols.
You are exactly right. The PLC doesn't know what an identity token is, so you absolutely cannot do pure end-to-end zero trust down to level 1.
So what's the alternative?
But what you can do, and what the modern frameworks mandate, is apply zero trust network access ZTNA at the boundary, specifically in the IDMZ. Okay, let's do a showdown of the access tools here. Based on the Sekamia source material we reviewed, we have 3 main contenders for remote access VPNs, SAS, and ZTNA.
Well, we already know VPNs are disastrous. They offer implicit trust. You authenticate once at the gateway and you are granted broad, sweeping access to the entire subnet. It creates the shadow corridor. It allows lateral movement. VPNs are dead for OT.
And what about SAS?
SAS, which is Secure Access Service Edge. This is the darling of Silicon Valley right now. SAS is incredible for IT. It combines SD-WAN and cloud-delivered security, but it is entirely too cloud-heavy for OT.
Why is that a problem?
SaaS assumes your workloads are sitting in AWS or Azure, and it assumes you have constant, high-bandwidth internet connectivity to run the cryptographic agents. OT environments are often physically air-gapped, offline, or located at the end of a terrible, low-bandwidth satellite link in the middle of the ocean. SaaS breaks down when connectivity drops.
So that leaves ZTNA, Zero Trust Network Access.
Yes, but it must be ZTNA, purpose-built specifically for operational technology. You replace the broad VPN tunnel with granular session-based access.
What does the ideal architecture look like for that third-party vendor who needs to remotely fix the robotics line?
Instead of a VPN dropping them straight onto the plant floor to talk to the PLC, the vendor connects to a dedicated, hardened jump host sitting in level 3.5, the IDMZ.
The buffer zone.
Right. They must use strictly enforced multi-factor authentication to even see the jump host. Once there, the ZTNA policy evaluates them. It says, okay, John from Robotics Co. is logging in. He is authorized to talk to exactly one specific IP address on the plant floor over exactly one protocol like port 443 for exactly 2 hours, and only because there is an open maintenance ticket matching his request.
That's microsegmentation at its finest. You've shrunk the blast radius to a single IP address.
Exactly. But here's the most crucial part for OT. You implement full audit logs and forensic session recordings on that jump host.
Like a video recording.
Literally like a video file. Every single click, every keystroke, every command John sends to the robot is recorded. If something breaks on the assembly line, you don't just guess what happened or rely on his word. You watch the tape. It turns a risky remote fix into an auditable, revocable, least privileged transaction.
That makes so much sense. It acts as a robust compensating control for the legacy gear that physically cannot protect itself. Let's pull this all together by detailing CISA's 5 priorities for applying zero trust in OT. Let's explain how and why these actually work. Priority 1, comprehensive asset visibility.
As we discussed, this means passive discovery. You deploy network TAPs. You mirror the switch ports to analyze the byte structures of the traffic without injecting packets. You can't apply zero trust policies if you don't even know the device exists.
Priority 2, zones and conduits.
This is the practical application of the Purdue model and IEC 62443. A zone is a logical or physical grouping of assets that share the same security requirements, like all the safety controllers in one zone.
And the conduit.
The conduit is the strict firewalled pathway between zones. Zero trust means inspecting every packet that traverses a conduit and denying everything by default.
Priority 3, identity and access controls. Specifically, the literature talks heavily about decoupling Active Directory. Why is that so critical?
Because Active Directory is the master key to the kingdom. If your IT and OT environments share the same AD domain, an attacker who compromises IT via a phishing email can forge a Kerberos golden ticket and instantly grant themselves domain admin privileges over the OT environment.
That's game over.
Decoupling means building a completely separate, standalone AD forest for the plant floor. If IT gets hit with ransomware, the OT network survives because the credentials don't cross over. Combine that with enforcing MFA at the jump hosts and you kill the always-on VPN threat.
Priority 4, supply chain risk management. This involves demanding software bills of materials, or SBOMs. How exactly does an SBOM help an OT engineer?
An SBOM is basically a nutritional ingredients list for software. Many OT vendors buy third-party code libraries to build their firmware. For example, the Ripple 20 vulnerabilities a few years ago involved a tiny TCP/IP stack from the 1990s that was embedded into millions of industrial devices.
They didn't even know it was in there.
Right. The end users and sometimes even the vendors themselves had no idea the vulnerable code was inside their hardware. An SBOM forces transparency. It tells the defender, this PLC contains this specific version of OpenSSL, so when a vulnerability is announced, you immediately know if you are exposed without having to wait for the vendor to figure it out.
And finally, priority 5, continuous monitoring and detection.
Using those passive protocol-aware OT tools to establish a behavioral baseline, OT traffic is highly deterministic. It's machines talking to machines on a regular schedule, so deviations are incredibly obvious.
So if a temperature sensor suddenly tries to reprogram a safety controller?
Exactly. The continuous monitoring system needs to instantly flag it, scream for human intervention, and potentially sever the conduit.
Okay, pulling this all together for you listening. The critical through line of this entire deep dive is that cyber risk in your operations is no longer just an IT problem for the basement server room. It is a fundamental existential business risk.
100%.
We are talking about protecting the physical world. The water chemistry, the power grid stability, the safety of human lives on a factory floor from the digital world. The air gap is completely gone. The M&M model of implicit trust has catastrophically failed us. We have to adapt to an architecture of continuous verification.
And I want to leave you with a final, somewhat chilling thought to mull over as you look at your own networks. If we reach a point where sophisticated state-sponsored malware like Stuxnet or Triton can completely spoof the network traffic, if you can no longer trust the packets on your network, and you can no longer trust the data on the HMI screen sitting right in front of your face, who do you trust?
That is the truly terrifying question. How do you defend against a lie you can't see?
I genuinely think that maybe the future of cybersecurity for highly critical industrial systems isn't in the digital code at all. Maybe, when everything else is compromised and the screens are lying, it means going back to trusting the raw physical process itself.
Wait, like analog?
Yes, using independent analog sensors, installing physical out-of-band pressure gauges that aren't connected to a microchip or a network at all. Because physics, unlike a Windows workstation, cannot be hacked.
Now there is a thought to keep you up at night. Trust the physics, not the software. That's all for this episode of Cybersecurity Under Pressure. Real attacks, real lessons. We went deep today, and honestly, untangling the mess of shadow corridors, legacy gear, and lying screens is enough to make anyone want to go entirely off-grid. See you in the next chapter.
Stay paranoid. It's not paranoia if they're actually out to get your OT network.
You have been listening to Cybersecurity Under Pressure. Real attacks, real lessons. Real incidents leave real lessons. Stay prepared, stay critical, and keep following the evidence.